Okay, hello everyone. This is the third lecture in topic 5.4. And today what we will be doing is we'll be continuing with our discussions on straight wire, and we'll extend that understanding to include a circular wire as well. We'll finish off with finding the magnitude of a magnetic flux density for a straight wire. And lastly, we'll also look at the directions of a magnetic field of a circular wire. So that'll be our task for today. Okay, so as you might all recall that we had talked about the directions of the magnetic field in a straight wire, which is carrying a current. Now, the way how we found out the field, the direction of the magnetic field, was basically by a rule. And that rule was the screw rule, right? Screw rule, or more appropriately, right hand screw rule. Okay. Now, the rule basically says that if you consider your thumb as a direction of the current, the curl of your finger represents the directions of the magnetic field. So that's what we said. And hence the direction of the magnetic field is shown clockwise here. Now, we also try to make a 2D representations of the magnetic field in a straight wire. So the 2 dimensions representation was basically as shown here. Okay, so in this case, what we said was, if we assume the current, if we assume a notation X cross as a current flowing into the page, then your thumb should be pointing inward, right, towards the page. So the curl is there towards the clockwise, so it's clockwise curl. So I can make my magnetic field direction in this way. Okay, similarly, in the second case where the current is flowing out of the page, because the dot represents the current flowing out of the page. So if you again consider a thumb, it's pointing out of the page, the curl is of the finger is anti-clockwise. So that's why you have the anti-clockwise directions for the magnetic field. Now, this is if we are considering the flow of the current, right? Now, sometimes it is better to represent the flow of the directions of the magnetic field instead of the directions instead of the current flowing. Okay, so that's what we will do next. So next, in the next section, what we will do is basically try to understand the magnetic field representations of the current carrying straight wire. Okay, I mean we'll make it 2D images for the magnetic fields in a straight wire. Okay, now let's consider a wire in which the current is flowing in the upward directions. And let's say this is also a perspective from the top, because you're looking at the wire at the top, from the top. So the question is basically then, how do we represent a magnetic field lines in this sort of situation? The answer is very easy. Again, right hand rule, the thumb points to the directions of the current, so which is up, that's good. Now, if you look at the curl of the finger, you see that towards the right side, it's going inward, right? So if I curl my finger, so it's going inward in this side, okay? And it's flowing outside in this direction. So if you look at the current, so inward is towards your right side and outward is towards your left side. So then, if the field is going inside the page, then then we represent it by a cross. So this is the magnetic field into the page. Okay, let me move this a little here. And so the second one would obviously mean that magnetic field out of the page. Now, I want you to understand the distinction here and the previous discussion. In the previous discussion, the cross meant the current flowing into the page, and the dot represented current flowing out of the page. But in this case, the cross represents the magnetic field into the page, and the dot represents the magnetic field out of the page. And now, because the fields are spread out, right? It's not only in one particular point. So the fields could be here, could be here, and so on. So that's why I could draw many, many dots as I want, or crosses. And it's not only in this line here, it could be above. Okay, so this is a very convenient way to represent a field, a three-dimensional field in a two-dimensional representation. Okay, so as soon as you see this figure, you can obviously say that the field towards the right is going into the page, and the field left of the wire is coming out of the page. So it's pretty convenient for us to draw the diagram. Now, obviously, the question could be then, what is the magnitude of the magnetic flux density around the wire? For example, what is the magnitude of the flux density at this particular point here? Okay, let me say at this particular point here, which is at a certain distance t. So from a formula perspective, we can say that the magnetic flux density B is given by a formula which is mu naught I over 2 pi d. Okay, so this is the formula that gives you the magnetic flux density. So let me erase this diagram here so as to make space here, where B represents B is the magnetic flux density. I is the current. D is the distance from the wire. Distance from wire. And mu naught is a constant whose value is 4 pi into 10 to the power minus 7 Tesla meter per amp. Okay, and this is basically called the permeability of free space. Permeability of free space. So this is the formula that basically helps us to find the magnetic flux density from the wire. Okay. Now the derivation of this formula is not required by the IB, so it's enough to remember the formula. Now the other question could be, what is mu naught here? Okay, I said it's the permeability of free space, but what does it actually mean? Think of it like this. The magnetic properties are more prominent in some mediums. Okay, so how effective is the magnetic field in particular medium is given by the permeabilities of that particular medium. So the permeability of the free space is the least effective medium that permeates the magnetic field. Okay, if instead of a free space you have a ferrous material, then the magnetic field would be more prominent in that particular medium. Okay, so you can think of the mu as that. Okay, so this is about the magnetic flux density calculations, the formula. So now let's do some calculations here. So the question is, find the magnitude of magnetic flux density at 0.5 centimeter, 1 centimeter, and 1.5 centimeter when the current of 10 amp flows through the wire. So in this question, I just want to show you that as you go away from the wire, the magnetic flux density decreases. So in order to calculate the magnetic flux density, the current is just 10 amp. So I'll just put 10 amp here and 2 pi times the d. So d is 0.5 centimeter. So let me just convert this into a meter. So I can just do 0.5 divided by 100. So I can multiply the 100 up like that. Okay. So you see here that the above values are a constant and 2 pi is a constant. So the only factor affecting the magnetic flux density here is the distance here. Okay, so basically then what I can say is flux at 0.5 is some constant, which I will just represent it by W here, divided by 0.5, right? And magnetic flux density at at 1 centimeter is basically then W over 1, right? And the magnetic flux density at 1.5 is basically W over 1.5. So you see here, as you go away from the wire, the magnitude of the denominator increases. So when the magnitude of the denominator increases, the value of the flux density here decreases. Okay, so if you're confused about what W is here, so W is just a 1000 mu naught divided by 2 pi. So I've just written it in a short form here so that it's easier to understand like this. So from the calculations, we know that B 0.5 is greater than B1 is greater than B1.5. So from here we have just shown that the magnetic flux density decreases as you go away from the wire. Okay. So now let's move on to the next section where we'll talk about the magnetic field of a circular wire. Okay, so now we'll talk about a circular wire. Okay. So now imagine you have a straight wire where the current is I, and you see the dot and cross diagram here, which represents the magnetic field. Now just imagine that this wire is bent. Okay, so when it's bent, it would look something like this, right? It would look something like this. Now the point is to notice that the magnetic field, okay, let's put it in the observation here. So the observation is basically that the magnetic field or magnetic flux density at the center of the wire. At the center of the wire is the highest, right? Because you see that all of the magnetic field here combine or superimpose to give you a bigger magnetic field at the center. Okay, and whereas you see in the outer, like the outer side, you see that the magnetic field decreases in the outer region here. So the main thing to observe is basically that when you have a circular wire, the flux density at the center is the highest. And we will also look at how to find the magnetic flux density at the center of the wire from a formula. So that's what we will do next. Takeaway point here, let me restate again. Takeaway point here is basically that when you bend a wire, it's basically like a straight wire, but when the straight wire is bent, the magnetic flux tends to add up at the center of the circular wire. Okay, it's maximum at the center. And the formula is a little bit different for the circular wire. Okay. Now, let's look at the formula or how to calculate the magnetic flux at the center. Let me again say our aim here is to find what is the magnetic flux at the center. So that's what we will be doing next. So the magnetic field or the magnetic flux density at the center of the circular wire is given by mu naught I over 2R, where I is the current flowing in the wire and R is the radius of the circle. So if you consider this as the center, then that is the radius of that particular wire. Okay, and mu naught is permeability of the free space. Okay, now let's try to do one question then. So we want to find the magnetic flux density, find the magnetic flux density at the center of the circular wire in which 10 amp current is flowing. Current flows. So basically what we just put in the values here, so B at the center will be mu naught times 10 over the radius. So the radius is, let us assume the radius to be center of circular wire, and the radius is basically, let's say, 1 centimeter. So if you have the radius as 1 centimeter, so just do 1 divided by 100, right? So you have like 500. Okay. So this is how you find the magnetic field at the center of a circular wire. We will do one more thing and we're done. After that, we're done with it to this lecture. So that is to find the magnetic field directions for a circular wire. There's an easier way to find a magnetic flux direction. Okay. So, okay, so let us assume this is a circular wire now. And we have a current that's flowing in this direction here like that. Okay. Now, in order to find the directions of the magnetic field, there are some tricks that you can use. So in this case, we could use a trick of something like this. If you consider a current that's flowing, excuse me, if you consider a current that's flowing in this direction, you can assume this as going like this, right? And this is like this. So when you combine these two, it sort of forms S. So that is what we call as a south pole. Okay, so that particular face of the wire that you're looking at is the south pole. Likewise, if you have a wire in which the current is flowing in the opposite direction, like this, then you can think of it as being something like that. Okay, so this is like a north pole. So the face of the wire that you're looking at should be a north pole. Now let us try to understand it in a little bit more detail. So I mean, like in dot and cross notations here. So if you ever get confused to how or in which direction the north is, you again can use the right hand rule. Okay, you can again use the right hand rule, and you can still find it. But in this case, now the right hand rule is slightly different. So right hand rule is slightly different in a sense that the curl of your finger, so curl of finger is the direction of the current, is the direction of the current, okay? And the thumb is the direction of the north. So in this particular case, okay, so in this particular case here, the current is flowing anti-clockwise. So what I will do is I want to curl my finger in the direction of the current. So it's anti-clockwise like this. So you see the thumb is pointing outside, right? So that means I'm looking at the north. So your thumb is basically the north direction. Okay, and likewise, if you look at this second diagram here, you will see that the current is flowing in the clockwise direction and your thumb is pointing inward. So which means the north is inside the page and the face that you're looking at is the south pole. So this is also another way to conveniently find the directions of the magnetic field. Now in terms of dot and cross, once you know the north and the south pole, it is pretty easy to draw the pretty easy to draw the dot and cross diagram. So in this particular case here, so let us consider a wire. Let's change our perspective of the wire right now. So let me draw a wire that looks like this. Okay, so this is like almost a side view of the wire. So if I'm saying that the current is flowing in this direction, right? I'm saying the current is flowing in this direction, then what? So the way how I find the north is basically by curling my finger in the direction of the current, and thumb basically gives you the direction of the north. So if you look at the figure there, my finger basically curls in the anti-clockwise and my north is to the right. So I will say my north is in this direction here and my south is here. Okay. Now, we all know that in a magnetic field, the field always goes from the north to south. So in this case, the magnetic field is in such a way that it circles the wire like so. So let me just draw almost excuse me. Okay, so the blue line here basically represents the magnetic field line of the circular wire, because the field line always moves from the north to the south pole, right? So you can have a field line that looks like this. So that with that we basically concluded with today's discussion here. So the circular wire will have a field lines that looks like this. Okay, represented by blue line. Now, let me just review a little bit on this last topic here, last section here, and after that we will be done for today. So if you have a circular wire here, so let me just draw a circular wire here. So if we have a circular wire here, and like the current is in the opposite direction here like this. Okay. Now, if you want to find the direction of the, like the poles of the magnet here in this circular wire, then what we do is we basically draw either S or the N. So if we draw an S here, you see that the direction flows with the current, right? So S here flows with the direction of the current. So this is the south pole. And in this case, if we draw a north like this, then you see that the north also, the figure N also follows the direction of the current. So we can say that the face of that particular circular wire is either a south pole or a north pole, depending on the directions of the current. So that's one thing we did. And also, what we said was if we consider a circular wire in slightly off angle like this, and I'll say that my current is flowing in this direction here. So it basically means that my south will be in the opposite side, okay, and my north will be here. Okay, this diagram and this diagram is identical, but it's just a perspective of view that's different. So this is the north pole, and if I want to draw a magnetic field of this circular wire, it basically would look something like this from north to south. Okay, so this is how we can figure out the directions of the magnetic field in a circular wire. We're done for today. I'll see you all in the next lecture. So in the next lecture, we'll talk about the forces between the two currents. We'll also talk about the magnetic field of the solenoids and so on. Okay, bye-bye.